Well, great. Then everybody, thanks for returning to the Vamos, and it's a real pleasure to have Jakob Reichel as our speaker today. Jakob is a scientist whose work I've followed and admired for many years now. Jakob did his PhD work in the group of Claude Cohen-Tanuji at the Laboratoire Kassler-Brossel at ENS. After that, he went as an assistant and then private docent and finished his habilitation while at the University of Munich and also the Max Planck Institute for Quantum Optics, working with Ted Hensch. And it's during that time that he really sank his teeth deep into the question of how to miniaturize and make more robust the experiments that we do on ultra-cold atoms. He's known for leading the first developments of atom chips and the first Bose condensation of atoms using an atom chip device. Following this, in 2004, he moved back to Paris, and he is presently a professor at the Sorbonne University and also a member of the LKB. You know, in my group, Jakob Reichel is known for his experimental acumen and also for one particular bit of advice, which is that the best thing to do with the degree of freedom in your experiment is to eliminate it. And so we follow his advice whenever possible. As you'll hear, Jakob does a range of research, all parlaying the use of advanced technologies to make more robust and miniaturized cold atom experiments. And it appears that as a source of inspiration, he also takes to playing chamber music in his spare time. But I think he will stick to scientific topics. Please, the floor is yours.
Thanks, Dan. Well, first, let me say that it's really this seminar is something special for me. I'm really glad to become part of it. You know, as maybe now this is has been born for the reason of this pandemic, but actually it's a response to something much more general. I mean, the COVID may be with us for another year or so, but CO2 emissions will be with us for much longer, and we have to find ways to maybe not to eliminate travel, but to travel less and still communicate as best we can. And this seminar, which makes me you know, brings me in contact with so many of you, is something that really you know, gives me some optimism for the future. So thanks a lot for having me here, and I hope I can entertain you a bit with what I'll be talking about today, which is spin squeezing in a miniature clock on a chip, where we get lifetimes of squeezed states, as you will see, that are a bit longer than what was possible before, and that will lead to surprises. So spin squeezing is interesting in many respects. I mean, of course, it's a quantum technology, and so it's part of these many endeavors that are underway to use quantum entanglement to as a resource to do something useful. But then it's also interesting in its own right, at least for you know, like old-fashioned fundamental physicists who are interested in questions like what happens when you have a system of spins, like in a cold atom system used as a clock, and now you have a lot of control over that system. You have long coherence times, which means that you have something like a magnifying glass for interactions. And among these interactions, there are the interactions among these spins, which we know can lead to rich and sometimes unexpected physics in their own right. Even when you start with a completely unentangled state of independent atoms. But now what happens if you take this system and now your initial state is a spin squeeze state, which is a many particle entangled state. That's a fairly unexplored region, but which we will inevitably get into as clocks progress further. And I mean, it's a point that people like Junier have been making for a long time, that the fermionic lattice clocks in particular, but also other very high precision clocks are actually a dream place to do many body physics. And so here I'm much more modestly, I'm not using fermionic lattice clock, but just a clock based on hyperfine ground states of rubidium. But even in those clocks, as you will see, that there's a lot of incentive to do spin squeezing. This is no longer a question that of interest only to a handful of quantum opticians. It's really now becoming a mainstream question, because quantum projection noise, which gets eliminated by spin squeezing, is becoming a real life issue in precision experiments. So let's take a minute to remind ourselves what this quantum projection noise really is. So in general, when you do a precision experiment, then you're interested in a phase measurement. But what you really measure is population differences. So in the end, you want to know that phase, which is a continuous parameter, but you have a finite number of atoms, each of which can only produce two different outcomes, which you can call up or down, or you can call 0 or 1, or you can call heads or tails, because actually the statistics that you get are exactly the same as in coin tossing, which is why, by the way, for me, this term of quantum projection noise always seemed a little bit pompous, because in the end, it's just binomial statistics, right? It's same statistics as in coin tossing. So so if these atoms are unentangled, each atom makes an independent decision between head and tails. You can be even in the absence of any technical noise. If you repeat a measurement, like for exactly the same phase value, you have it completely under control. Still, you will get fluctuations, because every time you repeat the experiment, each atom makes an independent decision, and that gives you these 1/√n fluctuations. That's the quantum projection noise. And this quantum projection noise has long been reached, actually. First time was in 1999 in a fountain clock at Zicht in Paris as well. And since then, one can say that quantum projection noise is a real life limit, and is becoming more so in other precision experiments as experimental art is advancing. And so one question, of course, that you immediately ask when you see the state of affairs is, okay, if you're limited by 1/√n, why not just increase n? But of course, that comes at a price. And in these clocks, for example, it would fatally increase these interactions that create, of collisional type that create shifts, and thus systematic effects in your clock. And in many platforms, it's like that. You have some issues that prevent you from increasing the atom numbers. In other experiments, it may be possible to increase atom numbers, and then clearly spin squeezing is not the thing to do. But there are clocks and other sensors, including the one that I'll talk about today, where increasing n is not an option, and as you approach quantum projection limit in these systems, then squeezing becomes very practically interesting. And so how does that work? Well, we said that the noise comes from the atoms being independent. So if you create a suitable type of quantum correlations between the atoms, then you can reduce that noise. And there are different ways of thinking about it, but for me, the one that you know, I find most fascinating is when you imagine that you start with a certain state that has a certain SZ expectation value, and now you measure the atoms one by one. Okay, so let's say you are in a 50-50 state, so you should have exactly 50% spin ups, but let's say that the 2 or 3 first atoms that you measure are all spin up. Now you're above average, and in a normal unentangled system, the 4th atom wouldn't be impressed at all and would make its random decision as before. But in a spin squeeze system, the 4th atom adapts its expectation value based on what you have measured before, and that's how you reduce the noise. And this is what is then traditionally represented on a spin n-half Bloch sphere, like this one here, where the uncorrelated state has a noise distribution that is, you know, here this circular blob, whereas in the spin squeeze state, you squeeze it in one direction, and then in order to satisfy Heisenberg uncertainty, of course, you have to increase fluctuation on the other axis. But as long as this doesn't wrap around the whole equator, this is not an issue if what you measure is the Z component. So that's the basic idea, and there would be a lot more to say about that. But for now, let's move on. And you know, I still have to tell you, I mean, and I pretended that it's not just a question for next generation lattice clocks. So to be a little bit more concrete, let's put that into perspective. Actually, there's a lot of atomic clocks in the world that are topics of research. I mean, one very well-known type are the chip-scale atomic clocks that work with hot vapors. They are in a stability range of 10 to the minus 10 fractional instability at 1 second. You can also buy rubidium clocks at 10 to the minus 12. They are very similar to the ones that are in GPS satellites. And next generation GPS satellites would like to go 1 order of magnitude lower. That brings you into the 10 to the minus 13 range, where there's no really satisfying solution so far. The clock that I'll be talking about is in that range. Not the best clock in the world, but a compact clock that brings you into that uncertainty range. And then, of course, all the way at the end of the spectrum, there are the optical lattice clocks, which are still 3 orders of magnitude better than that. So when you think about applying spin squeezing to such a clock, you have to compare these stability ranges, which generally correspond to Ramsey times as well. You have to compare that to what has been done so far in the you know, these beautiful experiments that showed us that spin squeezing is possible. Those were proof of principle experiments, and they did show that it is possible to perform squeezed clocks, but at stability scales that you can see here, which are not yet in this range of future compact clock or let alone optical clocks. And when you look at it from the perspective of coherence timescales, you know, the reason you couldn't go lower in these experiments is that coherence time, even for an unentangled state, was on the order of tens of milliseconds maybe. Whereas Ramsey times in such experiments here are typically closer to a second. So you need to gain about 2 orders of magnitude in coherence time. And when you do that, this will also inevitably bring new physics into play, because then you're more sensitive to smaller energy differences, like those that occur due to the direct interaction between the spins. This is a very active area of research. Just to give you an idea, here's a graph that I copied from this review paper here, where they put metrological gain with respect to the unentangled state of the same number of atoms as a function of the number of particles. And so you see it covers a very large range. For the clock experiment that we will be talking about, the interesting range is up here, where you have atom numbers in the range maybe 10, starting at 10 to the 3, maybe 10 to the 4, and as much squeezing as you can get. Maybe something like 10 dB would be nice. Not necessarily 20 dB in most clocks, because as soon as you have reduced by 10 dB, you will be limited by other effects, and further reduction by squeezing may not be visible. But anyway, so you see a lot has already been done on spin squeezing, and there are a lot of methods to create it. How do you do that? How do you produce a spin squeeze state? I mean that of course you need some form of interaction between the atoms, or at least some effective interaction, so you can entangle them. And one particularly beautiful and useful way of doing it is using an optical cavity. So optical cavity QED, that brings us to another big and exciting subject with a lot of ramifications. The flavor that we're interested in here is n atoms sitting in a cavity, and each of them has 3 relevant levels, 2 of which are the clock states, and the third one is connected through an optical transition that the cavity can either be resonant with or detuned from. And when you look at the coupled eigenstates of such a system, shown here in this diagram as a function of the detuning between the cavity and atom, the crucial point is that the energy eigenstates of these n atoms in the plus cavity are the so-called Dicke states, the states that have a well-defined number of spin-ups, or well-defined SZ of the global spin n half, if you prefer. That is something that can be said to the extent that the atoms are indistinguishable, so identically coupled to the cavity mode. And if that condition is fulfilled, or let's say effectively fulfilled, then you can think of the cavity as a Dicke state detector. And that is also the idea behind spin squeezing with the cavity. And I'm almost embarrassed to introduce that here, because there are people here who know more about that than I do. And you see Monica's name here, for example. And the 2 fundamental mechanisms that create spin squeezing using cold atoms in a cavity were both introduced in Vladan Vuletic's group around 2010, and they both follow from this mechanism of the cavity being having Dicke states as eigenstate. When you start with an ensemble that you place somewhere here on the equator, so it's a superposition of a few Dicke states close to the equator, right? So for each of these Dicke states, you have a different amount of light in the cavity, because each of these eigenstates corresponds to a different transmission of the cavity, and thus to a different field in the cavity, and that has 2 consequences. For one thing, you get a Dicke state dependent light shift, And this light shift now will lead to a Hamiltonian that does twisting on the Bloch sphere, and this twisting will squeeze the distribution. That's the in a nutshell is the idea of the cavity feedback squeezing. The other thing is that the cavity transmission, if you measure it in like shown here with a probe that is detuned with respect to the cavity resonance here, for example, and you measure just the transmission, then the amount of light that you get will give you information about the decay state, about SZ, and thus it will, as you collect photons, will start to project you onto a reduced uncertainty range of decay states, and thus you will know more and more about the about SZ. And both these methods, as I said, have been demonstrated and have been reproduced in other labs. In the meantime, there has been big progress, and noise has been reduced up to a factor of 100 below below the quantum projection noise, which is really impressive. So the remaining noise corresponds to only a handful of atomic spins. This is the mechanism that will be dominant in the experiment that I will show. So just once again, let's make sure we understood what's going on. So you have a detuned cavity. You are on the slope of the resonance. You're measuring the transmission of a probe beam, and the reason this works is that when you have these n atoms, each atom that is spin up will pull the cavity resonance one way, and each spin down will pull it the other way. So the exact position of this resonance here is what you want to measure, and you measure it by looking at the number of transmitted photons for known input pulse. Of course, then one thing that will introduce noise here is the photon shot noise. So obviously that works better if you increase the number of photons. But on the other hand, there are limits as well, because each photon has some probability of introducing spontaneous emission, and this spontaneous emission can change the spin of the atom that emits. And thus, you see that here there's a competition that will ultimately produce the ultimate limit of spin squeezing by Raman scheduling. Good. Yes. So I already said what is in this picture here. Another bit of fine print is that one thing you have to be careful about as well. These atoms are in the cavity, because we all started we started it all by treating these atoms as all equivalent, all indistinguishable, which is true if they are equally coupled to the cavity, but not quite that true when you have an atom like that one sitting here in a uncoupled region of the cavity. Now, another thing shown by Vladan's group is that even in that situation, the system still behaves like a system with identically coupled particles. It just reduces the effective number of particles, as long as you do all your measurements with that same cavity. What does not work is prepare your spin squeeze state like that in non-homogeneous system, and then measuring, for example, with a camera, those uncoupled atoms will then spoil the measurement. That's easy to see. Okay, but that was just okay. That's already the fine print. But it does it is an important point in practice, and one way to really ensure identical or almost identical coupling is to trap the atoms in a lattice that has exactly twice the wavelength of a probe. That is what Mark Kasevich did in that experiment that led to 20 dB squeezing. So the cavity is doubly resonant, and you arrange things such that each lattice side is is also maximally coupled to the probe beam. Good. So much for the squeezing and the state of the art. Now, in the remainder of the talk, I first tell you a little bit about the system that we are using, which is dubbed the TAC for trapped atom clock on the chip. We never built TIC, but now we have TAC. Excuse me. I'll tell you in particular some interesting spin interaction physics that we already observed that in that platform before we started doing spin squeezing. And then I'll tell you the recent experiment that we did to add a spin squeezing to that experiment. And this squeezing as you will see, is now a very long-lived spin squeeze state. And finally, in the end, I'll show you one first effect that we observed that arises due to this long lifetime, and that probably would have been present in other experiments too, if they had the coherence time to see it. Good. So this trapped atom clock on the chip, what is it? Well, the idea is just to miniaturize an atomic clock by trapping the atoms in a magnetic trap. And this magnetic trap is not just any magnetic trap, it's a trap on the chip. And that's what makes it so compact. Atom chips are no longer a new technology, so I won't say anything more about that, except for the fact that it gives you a versatile platform, and now you can even buy them from Gold Counter. It's a cool system, and we had shown a while ago already that in spite of the proximity of the chip, if you do things right, you can get very long coherence times. And that is actually something that we learned in precisely in this TAC experiment. The idea here is the following. The clock states that you use in such a trapped atom clock, it's not the m equals 0 state pair. You still use two hyperfine sublevels of the rubidium ground state, rubidium-87 ground state, but the states that you use are the f equals 1, m equals minus 2, and the f equals 2, m equals 1. That is something that goes back to Eric Cornell's work, who showed in the early 2000s that you could get a second long coherence times in spite of magnetically traveling the atoms with this level scheme. And we just picked up Eric's idea and applied it to a magnetic trap on the atom chip. And I could go on telling you how shifts compensate and so on, but I think we don't want to get into these details now. Let's just accept that in a certain range of parameters of very low temperature, you have a trapped atom cloud of around 200 nanokelvins, trapping frequencies that are such, trapping frequencies and atom numbers actually that are such that your density is about 10 to the 11 atoms per cubic centimeters, with trap frequencies of only a few hertz longitudinally and about 100 hertz transverse. Coherence times are long and where you can run the clock. And when we started doing that, came first surprise. We had actually done some crude simulations, and we expected a coherence time of 3 or 4 seconds. In 2010, when this platform came online, and we could start doing clock experiments in collaboration with CIRT. By the way, this experiment is located at CIRT, where the French atomic clocks are, and where they have excellent local oscillators and a lot of know-how. Here's Ramsey fringes that we observed, and you see that over this time of 5 seconds that we had, mostly limited by atomic lifetime, which wasn't much longer than that. The Ramsey contrast hardly decayed at all, and was much longer than what we expected. Now that's a surprise that you don't get every day, right? It's easy to get a shorter coherence time, but how do you get a longer one? It turned out that this was really quantum physics based on the exchange interaction. It really has to do with indistinguishable versus distinguishable quantum statistics in collisions, which lead to an effect that is something like a spin echo, except that you don't apply any pulses at all. So here's the basic effect. It turns out that when you are in a regime where your density is about where we are, and your relationship between trap frequencies, lateral collisions, is in such a regime that an atom can make many oscillations in the trap before it makes an energy changing collision that brings it on a different trajectory. Then what happens in this due to these due to the exchange interaction is this: if all spins are aligned, nothing happens. But if you have several different spins, like when you have dephasing, then your total spin is still conserved, because we're talking about forward collisions here, but the individual spins can change, and actually what they do is rotate about the total spin of the ensemble, which is conserved. And this is the effect that makes the that then serves you like a spin echo. So suppose now you have some dephasing in your system, and then you have this this effect that rotates the spin around their sum. This means that after some time, the spin that evolves more quickly than average, which of course was leading in the beginning, will now lag and will catch up with the other one, like in a spin echo. And that, of course, is true on certain time scales. And if you can do that before your lateral collisions will change the speed of spin evolution, or so transform this red spin here into a blue one, or vice versa. As long as you are in, this is why you have to be in this special regime. And as long as you are, then you have this internal spin echo compensating your dephasing, or rather not letting the system dephase in the first place, and that explains these coherence times here. And the smoking gun for these things, unfortunately, I don't have a slide on it here, is that actually you can observe coherence revivals. So contrast revivals are something that you get from this system, from this effect, that you don't easily get from any of these other effects that people in nuclear magnetic resonance are familiar with. Anyway, so we have this effect here, and it's the first manifestation of spin physics in this clock, and it was a beneficial one. And it can be quantitatively modeled, it turns out, from an equation that looks really classical. Here's the most simple version. So you have a total spin. This vector here is composed of the expectation values of the Sx, Sy, Sz. And yeah, what I didn't stress enough maybe is that we are in a situation where the dephasing speed of a given atom depends on its energy. In our case, that's because these atoms oscillate in the trap. The trap does cause a little bit of level shifts, and therefore a very cold atom that spends all its time in the middle of at the bottom of the potential doesn't have the same dephasing as an atom that has a high motional energy. And explores the higher magnetic fields in the periphery. That was the reason in this particular experiment. But as soon as you have spin evolution, dephasing depending on some parameter, which is energy in this case, and you are in the regime of densities that that we said. Then you can start from full quantum equations and arrive at this classically looking equation where you see that now it looks like a torque equation where the spin is rotated about this integral here, which is nothing but the energy weighted average of the spin distribution. Okay, so that's the equation version of what I said. The spin's rotating about the sun. And in this experiment here and its siblings, this rotation rate is on the order of a few hertz. Another way of looking at that, that Kurt Gibble has been pointing out for a long time, is that you can also see the same physics arising from the particular values of scattering lengths that you have in rubidium, and which make that when you look at a pair of atoms, you have an energy difference between this state here and this state, which leads to to some it displaces this state, and actually this rotation rate, this exchange rate here is nothing but this energy difference here. So this shows up the connection to the physics of fermions in lattice clocks, but I won't use it in the following because it's more difficult with this, starting with this model to get an intuitive picture of what your spins are doing. Okay, I have to speed up a bit. So we also measured, of course, the stability of our clock. It's in the mid-10 to the -13 range per second, and it integrates down quite nicely. That's all we need. So we are in a metrologically relevant regime here. And when we look at the contributions to this measured stability, we find that we can model it quite well, and that the quantum projection noise in red here does make one of the most important contributions to it over a wide range of Ramsey times. And one appealing thing is that if you remove that, then your error budget changes in such a way that the accessible range, where the total stability is rather flat, becomes much larger. So now you can, once you have eliminated that, we could go to much shorter Ramsey times, for example, which are technically more appealing because you increase your bandwidth and so on. So spin squeezing is not just about making it the clock more stable. It's also about bringing it, changing your parameters to increase bandwidth or reduce other sources of error indirectly. Good. So now we wanted to bring cavity-based squeezing to this clock. How do we do that? Well, our take on it was Dan mentioned that I like miniaturization, so we developed a miniature cavity. I don't have time to say a lot about it, but it's based on laser machining optical fiber tips, such that you get miniature mirrors, and then two of these machined fiber mirrors face to face make a Fabry Perot that is both miniature, very high finesse, and has a small waist. You do that by with CO2 lasers, so it's not even very complicated. It has been adopted by a lot of groups working in fairly different regimes, and we have a lot of fun collaborating with colleagues who do vastly different physics. But today we will use such a cavity for the spin squeezing. One problem we had to solve to go there was to make these mirrors actually a larger radius of curvature. But I won't go in those details here. We just say that in doing so we also learn to make more complex shapes, but that's another story. And so okay, once we have our two fiber mirrors, now we have to somehow combine that with the atom chip, and here's the chip that we came up with. That was the thesis work of Konstantin Ott. So the idea is the following. So you have this atom chip, which is like 40 millimeters on the side. Here are the wires that are used to produce the cold sample and trap it. We first trap it here, and then and then we bring it around here. And here is you see here are two fibers coming in and two from the other side, and they form two Fabry Perot cavities that you see slightly better here. Here so you see the fibers coming in. These are piezos used to tune the cavity resonances. And here are these fibers, and you see this cavity for our on our scales is really a long cavity with a bit more than a millimeter, and we need it to be so long so that we can fit in this trapped sample of relatively low density cold atoms. So first this omega-shaped wire is used to you have a mod here, you bring these atoms there, and then you parallelly displace them into the cavity, and then you're ready to use the cavity. And you also have on-chip wires to excite the clock transition so that you can do Ramsey spectroscopy. So that's our platform, and here's some more data. The cavity is not even very high finesse. Actually, the cooperativity is on the order of 1. Cavity line width, something like 46 megahertz. And the atomic ensembles that we use are typically 20,000 atoms with a cloud size that is 9 microns transverse, which needs to be compared to the mode waist, which is larger, but not orders of magnitude larger than this transverse dimension. And then we send in 780 nanometer line that we measure with a single photon counter in transmission, and that's where our signal will come from. Okay, so
Jakob, before you get to results, can we pause and ask one question from the audience?
Yes, this would be the place. Maybe now before we come to the squeezing, would be a good place for if you have questions about that so far.
Yeah, so there's actually one question that leads into this very nicely from Brandon Brinkemeyer, who asks, why are you choosing this method of squeezing over others? And are there certain limits where one method is better than others? And I think particularly the question is probably about this cavity-based squeezing as opposed to other techniques you might imagine.
Yes, so cavity squeezing as opposed, okay, what else could you do? You could do squeezing based on atomic interactions. That works very well in BECs. But as it is based on interactions, it also leads to shift. And so in a clock, it's probably not the way to go. Actually, we tried running our clock with a BEC, but it's difficult to keep the interactions under control. And so light is better. You can think of it as an effective interaction that you can switch on and off, and so you only get it when you want it. You could also ask why we use this particular type of cavity interaction and not the other one. That's a more difficult question. We started with it because for some reason we thought it was better. I'm not even sure it's true. I think the last word isn't said between the you remember I showed these two interactions or two mechanisms that are at work when you do cavity squeezing, and I don't know if I can't say something very general about that. They both work well.
Great. So then I think in the interest of time, we'll let you continue and hold other questions till you stop again or are finished. So great.
Okay. Yeah. So now for the squeezing, actually, I will be rather quick because we are doing it in quite exactly the same way that it has been done several times before. So first of all, of course, you have to be very careful about your absolute calibrations and all that, but I'll spare you these bookkeeping things. Then first thing we did was to make a cavity probe pulse, determine SZ from the cavity transmission, and compare to what we get from our camera. We have a fairly good camera, which also allows us to measure the number of atoms in each spin state with a noise that is close to quantum projection noise. And to within the noise of this imaging, here you see the correlation between the two. It's actually limited by the noise of the imaging, but to within that limit, it's okay. That's encouraging. And so now, how much noise do we actually have from the cavity probing? Well, the main noise source of cavity probing is simply the shot noise of the number of photons that you use. So as a function of the number of photons, here's the shot noise limit. And if we probe with the empty cavity and look at the statistics of our transmission, we find that we are actually close to that limit, which is a way of confirming that our cavity log is okay and we don't have too much systematics in that part. Now let's put atoms into the cavity, do a pi/2 pulse to put them on the equator, and then do a cavity measurement. And then we find here, okay, here's a sample result as a function of the number of detected photons. We find something that is compatible with the quantum projection noise, which is what you expect if you did your calibration well, and so on. So we do have this noise, and this noise comes simply from the fact that you project that state in a way you do it atom by atom. Okay, so now what happens if you do a first probe pulse that projects you, and then another identical probe pulse? Then what you should find is a result that is very close to the one that you found first time. Okay, so if you do that, then you verify that your measurement is actually a quantum non-demolition measurement that projects you onto a state, and next time you measure, you find the same thing. Of course, you can't expect to be better than photon shot noise once again. And actually, we don't quite reach that limit, but we get relatively close to it. So what you see here is for an ensemble of 23,000 atoms, comparing from the variance, the fluctuations of these repeated measurements, and you see that we can get quite far below the quantum projection noise. So that's nice. If we want to know how good that is for actually doing a clock measurement, you can't stop here yet, because you also have to take into account that you do create some side effects, which in essence boil down to reducing the effective length of your spin. In other words, you have to also measure the Ramsey contrast after you've done this projective measurement, and then you taking these two things together, your contrast and your measured number squeezing, then you get your metrologically useful squeezing. And in our case, that as a function of atom number, as a function of photon number, and for this atom number here, looks like that. So it first goes down as you increase the number of photons, and then goes up again when you use too many photons, because these photons also have side effects. And here at the best points, it's something like 8 dB of metrologically useful squeezing. So that's far from being a record, but it's good enough for us. If we can use that in a clock measurement, then we will be very happy, because it will reduce quantum projection noise to no longer play a big role. Okay, so far so good. Now, what sets our experiment apart from the previous ones is that we also have this very long coherence time. Actually, in this experiment, we measured, in spite of the presence of the cavity and all that, a coherence lifetime of about 20 seconds. So what happens now if we project onto a squeezed state once again, and then we wait longer and longer before we do the second measurement? That's where it gets interesting. That is something that previous experiments have been able to do for, maybe 10 milliseconds, but not for the timescales that you see here. And now what is shown in these graphs? What we show here is raw data. So you see the cavity detuning that we measure in the first pulse, and then for the same ensemble at one data point shows what you find for the second measurement. And the fact that, okay, for these short delays, TD here, they fall on a straight line with slope 1, as you expect. As you go for longer times, they are still very correlated, as you can see here, but the slope has increased. Although we're doing exactly the same measurement, we now get more signal from the same atoms, as if you had it put in an amplifier somewhere. You get more signal per photon. Now that came as a complete surprise to us. And what I'd like to tell you now is how we can explain that from the spin physics that we've discussed before. And so let's call okay, phenomenologically we have this amplification factor here. We can measure it for every time TD, and we can plot it as a function of this time, and then you see that it first rises up to something like 300 milliseconds, then it goes down again, but remains larger than 1 for about 1 second, and then up to 2 seconds we can still measure, but no longer see amplification. And this gray curve here I'll come to in a few minutes when I have explained to you how we think we can understand this effect. So what is that due to? Well, you see, in the way we do the squeezing with the cavity, we do introduce some inhomogeneity. The atoms, as in what I described previously, have some oscillation or amplitude in the trap. And although on these timescales of 1 second, you know, the dephasing by the magnetic trap that I talked about before doesn't play a role, we can completely forget about it. We still have these atoms oscillating in the trap, and so those that have a very small oscillation amplitude transversally will be well coupled to the probe profile, whereas those that oscillate more have a lower average coupling. Now we take care to make all our probe pulses equal to the oscillation period, so that we always average over 1 period at least. But nevertheless, depending on motional energy that a particular atom has, it will have a slightly different coupling. You know, it's on the order of 10 or 15%, but it's still there. And so what is the effect of that? Well, if you start with these atoms on the equator, as you remember, because this is squeezing by measurement, every time you do a probe pulse, you will get a slightly different result corresponding to the value of SZ compatible with the initial quantum fluctuations that you measured in that particular instance. That means that in some instances you will get above average a number of photons in the cavity, or in others you get less. And the dephasing that you get between the atoms depends on that. And it turns out that the way we do the probing, if SZ is larger than 0, the well-coupled atoms will lead, whereas if it's smaller than 0, they will lag. And this is something that is actually in very similar ways is present in all spin squeezing experiments with cavities. It's just that usually, you know, you don't read out that information. You do have that form of dephasing. You reduce it by using you know, composite pulses and spin echo sequences and the like, but you still get some of it. And so you do create a correlation now between your atomic energy and the dephasing. And this dephasing also depends on the measured value of SZ. And that's the crucial thing. Because when you look at what you now get after ISRE, after this spin exchange interaction, which now rotates the spins about their sum, it turns out that everything acts in just such a way that the well-coupled atoms shown in red here, which dominate the measurement result of the cavity, those well-coupled atoms are rotated in such a way that if SZ was already larger than 0, the SZ of these particular atoms will be still larger. And if SZ, the measured SZ was smaller than 0, then the one of the well-coupled atoms will be still smaller. And then because these atoms might make above average contribution to the measurement because of their better coupling, this is what amplifies the measurement. So this is our hand-waving explanation of the effect. We can turn it into a semi-classical model that doesn't contain spin correlations, but contains the spin dynamics that I just described. And but of course, I need to convince you that this is actually the right explanation, right? And actually, one thing that this model predicts here is that we should now have a correlation between the motional energy, let me call it the temperature of a given atom, and its spin expectation value. Okay, a cold atom, shown in red here, should have a spin expectation value lower than average if the measured SZ was smaller than 0 and higher otherwise. Generally, you see that this effect gets stronger the more you turn. So the longer you wait until if I go back here, until you reach a quarter oscillation period of this exchange interaction. And now let's look at that, because we can measure that. It turns out we can measure that with our camera. We can make a spin resolved measurement of temperatures. And when we do that for these short times, here's the temperature measured selectively for the spin up atoms. And on the x-axis, you have the measured results of the cavity. No correlation for the short times. And as time passes, here for 250 milliseconds, you see that the correlation indeed establishes between the temperature and the cavity measurement, as predicted by our simple model. And you can also look at the temperature fluctuations measured for longer and longer times, and you see that it evolves in the same way as this amplification factor that we observed, which is also what you expect from the model. And we can turn that into something semi-quantitative by putting this spin torque equation into a numerical simulation with exactly the parameters that we have in the experiment. And then this is what you get. And you see that it does reproduce for times up to a few hundred milliseconds qualitatively the behavior. And it even gives a reasonably good quantitative estimate of this amplification factor, which is really more than we expected. Then for longer times, it doesn't reproduce what happens. This is certainly partly due to the fact that we do have lateral collisions that screw up the atomic trajectories, but it's also certainly due to the fact that the quantum correlations are not contained in that model, and they must play a role as well, right? We have not taken that into account yet, and so, but given the simplicity of the model, we were already surprised how to get this relatively good agreement for these times, which are still as long as several hundred milliseconds. So armed with that, we can now look at the long time evolution of the spin squeezing itself. So here once again is what I call the number squeezing. So just the correlation between the SZ results, and you see that I mean this is what you expect for quantum projection noise. Quantum projection noise value here goes down because the atom number we have losses in this in the system, but you see that for several for up to 800 milliseconds or so, you stay quite close to the minimum that you can have due to the initial cavity measurement, and then you get deviation. And that was a number squeezing. When we factor in the contrast, this is what we get, the red points. That's the metrological squeezing, so it remains below 0 dB for times almost up to a second. So in that sense, we have metrological squeezing for for many hundred milliseconds here, and that's really good news for the clock physics that we can do. But it also gives us new riddles to resolve. You see that we find something here that is below this theory curve. What is this theory curve? This is what you expect from nothing but the fluctuations introduced by losses. You have collisions that kick atoms out of the trap. This will reduce the squeezing. And from that alone, we would expect to be on that line, but we find results below. How is that possible? Is that something that we don't understand? Is that does it have to do with finer quantum effects? We don't know yet. So that brings me to the end. So in summary, I would say, okay, we from a metrological point of view, we are happy to now have long-lived squeezing available in a metrological platform where we can actually apply it to a clock measurement, and this is the next thing that we will do now. From a more fundamental perspective, you know, I would see it as one more instance where quantum correlated atoms plus metrological sensitivity give you new and surprising effects based on interactions in a many-body system. And while our semi-classical model gives first insights, full quantum model is clearly needed, and it will be interesting to explore that and see how it is related to physics in lattice clocks once again. So that's the end. Thank you for your attention, and I'd like to acknowledge my fabulous group, and in particular the people who worked on that experiment. On the SIRT side, the leader is Carlos Garrido Alzar, who took over from Peter Rosenbusch, who is no longer at SIRT, and Miles Mengzi Huang was the lead PhD student who established most of these squeezing results, aided in the first phase by Tommaso Mazzoni, who was a postdoc, and now we are happy to have been joined by Alberto de la Paz as a PhD student, and we have a postdoc position available if anybody's interested. And that's the end, and I hope we still have a few minutes for questions. I'm sorry for having been a bit too long.
Well, we certainly do have some questions. So yeah, let's thank Jakob, and then I'll ask a few questions here from our listeners. Maybe a good starting point is to tell us a little bit more about what limits how much squeezing one can achieve. This is from Rui Zhang, and obviously you showed us already that there are some things where you get even better squeezing than you expect, so perhaps we don't know the full answer, but if you could talk a little bit about that.
Yes, okay, so there are several things here. I mean, I mentioned the limit due to Raman scattering. That would rather be in the 20 dB region, so we're not even close to it. So we have several effects contributing here. Some are technical, like the fact that we, you know, there are phases that we could correct, but we don't, because we don't have real-time correction pulses yet. But there are also more fundamental things. You know, I mean. We have these phase shifts induced by the photons that are possibly a bit more complex in our to handle in our system than in a ideal system, because you see, as soon as we create a little bit of dephasing during the pulses, ISRE, spin exchange dynamics, sets in and starts to rotate these spins. And even if we then do a composite pulse, whatever has happened inside this composite sequence is not perfect, and this certainly contributes to the limits. Well, there's more to say, but that's the first thing.
Great. So we have a couple of questions about your cavity design. So Bill Phillips asks, really small cavities make one think about having high cooperativity. Does it matter? And related to that, John Simon was asking why there are two cavities and whether one is for experiments requiring higher single particle cooperativity.
Yes, John is perfectly right. I mean, the other one has a higher cooperativity of a few dozen, and the idea was, you know, there are ideas about using cavities in other ways to improve clocks, and that's why we inserted the second cavity. You know that. There's this idea introduced by Philippe Bouillet in particular, where you try to do real-time feedback on your atoms as the Ramsey sequence proceeds. That is one thing you might try to do. There, the idea is to prevent phase slips. You know, one thing that can happen in a clock is that your phase estimate is off by 2 pi, and at long Ramsey times you can try to avoid that from happening by continuously monitoring with weak measurements, and that's one thing you can do. And then, yes, I mean, there was room for 2 cavities, and we had a few vague ideas, so we just put it in. We haven't used it yet too much. Another more technical thing is that you can use the high finesse cavity to lock the low finesse one, so that you can use the low finesse one without any locking light inside, which is good for the clock.
And so just following up a little bit on that, Joe Goodwin asks, what would an ideal cavity for spin squeezing look like in terms of G kappa and physical size?
Well, I think that okay, so in terms of G and kappa, that it turns out that you want a cooperativity close to 1. You want a cavity that is sensitive to small fluctuations, of course, but still you also need to be able to detect the largest expected fluctuations, which are square root of n, and that means that that's why you don't want a super high finesse cavity. Now, what makes a cavity ideal, I think, goes beyond these cooperativity requirements, which are pretty modest. Depends on what you want to do. You see, we observed an effect that looks interesting and beneficial, although it comes from inhomogeneity. There are 2 takes that you can take on that. You can try to employ it in the clock. This amplification effect that we observed, closely related to what you, Monica, pioneered in, and which goes by the name of quantum phase magnification. You can try to exploit that. And an interesting question is, you know, I mean, in our, you remember we had these 2 measurements. The second one is more sensitive, so you get more information per photon. So the role of photon shot noise is reduced there. Now, how all that you know, would need to be taken into account in an ideal cavity is whether you want to exploit such effects, or whether on the contrary you want to say, okay, I want the cleanest system possible. I don't want any dephasing in the first place, in which case you would need to use a larger cavity waist. You wanted, yeah.
Great, yeah. So maybe I'll move on to a couple of questions about the spin self-rephasing and also the amplification effects related to that. So Jing Wu asks how sensitive the spin self-rephasing is to the density of atoms. And Shimon Kolkowitz also asked to what extent the exchange interactions, you know, that help preserve coherence also result in density shifts that affect the accuracy or the long-term stability.
Yes, yes, it's a function of density, and so the spin exchange rate depends on it, but the shifts depend both on density and on temperature. And it turns out that for us, it's the most crucial thing in terms of keeping shifts under control, you know, whether we squeeze or not, that is the temperature. So if you keep the same number of atoms, same cavity parameters, but your temperature has even very small shot-to-shot fluctuations, that means that your collisional shift will also fluctuate. And that can be corrected to some extent, but not perfectly. and that is one of the main sources of long-term fluctuations in our system. We see the air conditioning in our clock, and the way it gets into the system is, we think, due to temperature fluctuations of our sample. Not that we use the air conditioning to cool the atoms, but I mean, you see what I mean.
Right. So related to questions about temperature, Bill Phillips asked, he has actually a two-part question. If the trap were perfectly magic, not affecting the clock frequency, how would that change things? But also, what if the atoms were cold enough to be in the ground state?
Okay, so if the trap was perfectly magical, for the results that I have presented today, it wouldn't change much, because the dynamics that we've been seeing of this amplification happens on a shorter time scale. So the dephasing that triggers the ISRE in this experiment comes from the cavity light, not from the trap. Okay. On longer time scales, then you also have the non-ideality of the trap kicking in, and if the trap was completely magic, that would be great, because it would allow us to make an absolute frequency standard, which we can't now because we have to correct for shifts. And what was the second half?
What if the atoms were cold enough to be in the trap ground state?
Yes, I mean, it would be great if they could be still colder, but without condensing. If they condense, then once again the density goes up, and then and then you get density effects that are really hard to keep under control. As I mentioned, we try to run the clock with a BEC, but then you really get shot-to-shot fluctuations that that make the clock stability orders of magnitude worse. And if you could be still colder, or at least have no temperature fluctuations at all from shot to shot, that would be a major advantage for using this for the long-term stability of that clock. And by the way, from the clock perspective, these clocks that are in this 10 to the minus 13 per second range, there are a lot of clocks that attain this regime at 1 second. Where they all have problems is for the long-term stability. And ours is not the worst for that. It's actually quite good. But like many others, where it's actually not ready for applications is in its long-term stability.
Great.
Yeah,
so
as I said, that's related to temperature mostly.
So we have a question from James Thompson, who first of all says congratulations on beautiful results.
Thanks, James. I'm happy.
To see the amplification effect, do I need 4 ingredients? QND measurement, so quantum non-demolition, probe-induced SZ squared during the first probing, inhomogeneous coupling to the cavity mode, and spin exchange interactions during evolution.
Yes.
So the question is, do you need all 4 of those?
Well, what would happen if you didn't have the projective measurement in the beginning, but another form like one-axis twisting? That's a good question.
Or actually, maybe to add to that question, so I think one effect you mentioned is there's a probe-induced phase shift, right? There's inhomogeneous coupling.
And that's still there.
Spin exchange interactions are key, but do you also need a cavity-mediated, a probe-induced twisting interaction? That was a 4th ingredient that James cited. Or is it sufficient to have the inhomogeneous AC Stark shifts and the direct spin exchange?
A cavity-induced
SZ squared interaction.
I don't think you need that if you have if you have the projective squeezing in the first place, plus the dephasing that goes with it. Then ISRE will do the rest.
Great, thanks. So I think we are running low on time, so I'll just conclude on one more big picture question from Bill Phillips. which is that while there are lots of great demonstrations of lots of squeezing, he says, if I understand correctly, only advanced LIGO uses squeezing to do something that could not be done in any other way. So the question is your squeeze clock in that category? And if not, what will make it so?
Well, I mean, like, yeah, so that is squeezing with photons, right? Squeezing with atoms hasn't been used in anything that can be really called an application yet. And in our clock, I mean, we still have to do the squeezing enhanced clock measurement. And when we've done that, then Bill, I can answer your question. But one thing that is true is that with the help of the squeezing, as far as we can see now, our particular clock will be able to do something that we couldn't do without it. And what that is not simply staying at the same Ramsey time and getting better stability. It would be to trade in this gain in stability for shorter Ramsey time, because shorter Ramsey times have a lot of advantages. Some of them technical, and some of them due to the fact that then your local oscillator noise doesn't contribute that much. And so you will gain, once again, in a way that is not in these simple models. And that is something, that is of great practical importance, I think. These local oscillators are as much an issue as the physics package itself. And there, I think there's a real very concrete advantage that hasn't been publicized a lot yet in the literature.
So with that, let's thank Jakob one more time, and I'll hand it back to Dan to conclude here.
Thank you so much for coming. Great experience, and for your questions as
well. Thanks again, Jakob. Can you guys see this? Right. So I just want to let you know about the talks that are coming this next week. The Quantum Science Seminar, which is hosted by our colleagues in Europe, will feature an American speaker, Jun Ye, who will be talking about the Fermi gas of polar molecules from 3D to 2D. And the VAMOS seminar, hosted here in the US, will be featuring a European speaker. This will be Tilman Esslinger, talking about driven and self-driven quantum many-body systems. I look forward to seeing everybody at these two seminars this next week. Take care.